Somebody takes to Reddit to claim that something is being done universally incorrectly. Oh, this isn't gonna end well, is it? Why is the antiderivative of 1 over x universally taught incorrectly? This is something that would be taught in a high school calculus class. We're going to take a look at this complaint and the relevant discussion. Is something actually being taught incorrectly in a negligent and widespread manner? If you know calculus, you can see the OP's point here, but if you don't, it'll take just a couple of minutes to explain the issue, and I'll be curious to hear how all of you were taught about this in the comments. To understand the issue that OP is raising here, you need to have a rough understanding of derivatives and antiderivatives. You don't actually need to know what ln x is, but we'll go over it in brief anyways. But let's start with derivatives and antiderivatives, a little bit of flirting with calculus. The derivative of a function f is, roughly speaking, another function which gives us the slopes of f at its points. Here's a lovely function I might have with the name of f. And again, the derivative of f would tell us the slopes of this function at its various points. For example, over here, the slope is quite steep. It's shooting up very fast, so the value of the derivative would be large and positive. Up here, the function actually reaches a maximum value, and the slope for just a moment is 0, hence the derivative would be 0. For just a moment, the function flattens out and then starts to decrease a little bit. Over here, the function is decreasing slowly, so the derivative would be slightly negative. That's a slight negative slope. Over here, it starts to increase slowly, so the value of the derivative would be slightly positive. Understanding what we mean by slope when we're looking at a curved function like this is not trivial. Things are very straightforward, pun not intended, if we look at a line. Here's a graph of the line y equals 2x plus 4. What's the derivative of this? Well, like we said, roughly speaking, the derivative gives us the slopes of the function, and this line has a constant slope. Its slope, of course, is 2, you may recognize from slope-intercept form. So the derivative, which we would often write as y prime, is equal to 2. Big difference between this function and this one is that with the line, the slope, and thus the derivative, are constant, whereas in this function we saw that the slope and thus the derivative change depending on where we are on the function. Here's another line, which in a way is even more simple. This is just a constant horizontal line. This is a graph of the line y equals 4. The slope of this line is actually 0. It's not increasing, it's not decreasing, it's totally straight, and so its derivative, y prime, is 0. It has a slope of 0 because it's not going up or down. I hope you'll forgive my hideously written y's, but as you can see, slope is a very simple concept when we are looking at lines. So going back to the curved function where the definition of the derivative is a little bit more up in the air, we characterize it more formally based on the slopes of lines. I said roughly speaking, the derivative is the slope of the function at its various points. But now, to speak less roughly, what we mean by slope is the slope of the tangent line, a line which serves as the best linear approximation of a function at a particular point. At this point, the best linear approximation is a very steep line with a very big slope. However, at this point, the best linear approximation is a very flat line with a slope of 0. If we look at this point, the best linear approximation of the function at this point is a line with a slight upward slope. It's the slopes of these tangent lines which are the derivative of the function. So that's the derivative. But remember, the thing that's being universally taught incorrectly is the antiderivative. What's that? Well, it's exactly what it sounds like. It's just like the derivative, but its heart is filled with dark energy and yearning for malice. Speaking more formally, the antiderivative is the inverse of the derivative. Like we said a minute ago, the derivative of 2x plus 4 is 2, because the slope of 2x plus 4 is 2 at all of its points. Notice how the only relevant number in the function is the 2. That's the derivative, the slope. The plus 4, which is the y-intercept, in effect it's a vertical shift, this doesn't actually affect the slope. Of course not, right? Because it doesn't matter if I take this line and move it up or move it down, its slopes are of course the same. So then, if the derivative of 2x plus 4 is 2, what is the antiderivative of 2? Let's repurpose the letter f here and say that f of x is this function that's always equal to 2. What is its antiderivative? Well, certainly it should be some function we might call big F of x, so that if we take the derivative of this antiderivative, which we can write with the little prime there, the derivative should give us back that function little f of x. The antiderivative of 2 should be a function whose derivative is 2. So then, of course, big F of x needs to have that 2x, which gave us that slope and thus derivative of 2. But what about the plus 4? Well, like we said, the plus 4 doesn't have any bearing on the slope, so there wouldn't necessarily be a reason to have a plus 4 here, or plus any other particular number. No matter what number we put here, if we take the derivative of this function, we're going to get 2, as desired. So what we do is write a plus c. The term of art is that this is an arbitrary constant. This represents the fact that we could add any constant number we like, and the derivative would still give us 2 just as desired. The constant could be plus 4, it could be minus 10, it could be plus 0. In any particular case, it would have to be one single number, but it doesn't matter what that number is, and so the general solution would be 2x plus c. Now, for derivatives, there is a lot of notation. This prime notation is very popular, but a notation that some of us like even more is this dx notation. This says we're taking the derivative of some function with respect to x. Now, we need to talk about the derivative of the natural log function. However, to talk about this, let's just briefly introduce this natural log function in case you haven't seen it before. You know how, roughly speaking, if you have x squared, so a variable to some number power, you can undo that squaring by taking a square root. So if x is positive, the square root of x squared we know is equal to x. The square root undoes the squaring. But what if the roles of the variable and the constant are swapped? What if we have something like 2 to the power of x? This is a much different situation, and the square root is not going to solve for x in this case. The inverse of a function like this, where the variable is in the exponent, is a family of functions called logarithms, and lnx, the natural logarithm of x, is just such a function. Like I said, it's a family, and this is not the member of that family which undoes 2 to the x. Rather, lnx is the inverse of something called e to the x. E is just another special, irrational, transcendental number, just like pi. It's very cool, it's very special, it's very handsome, it's connected to finance. All you need to know for this video is that it's a number, much like pi is. So if I take e to the x and I put it in this natural log function, the natural log undoes this exponentiation process, and the output is the number x. Exponential functions like e to the x and 2 to the x grow very, very quickly. For example, 100 is not that big of a number, but 2 to the power of 100 is massive. Since logarithms, like the natural log, are inverses of exponential functions, it shouldn't be surprising that they grow very, very slowly, the opposite of exponential functions, which grow very, very quickly. In fact, 100 is not a super big number. 10,000 is pretty big. The natural log of 10,000 is only about 9.2. This is because that special number e must be raised to a power of 9.2 to get 10,000. And with that in mind, there are some restrictions on what we can put into this natural log function, what we call its domain. If we're going to plug some number x into the natural log function, that number better darn well be positive. Remember, we said the natural log of 10,000 is about 9.2 because e to the 9.2 is about 10,000. But there's no power we can raise e to get 0, so we can't plug 0 in here. Similarly, there's no power we can raise e to get a negative, because e is positive, so we also can't plug a negative in here. Just like 2, you can't raise 2 to any power that's going to make it 0 or negative. just doesn't happen, so we can't plug negative numbers or 0 into the log function. And all of these properties we've discussed can be observed in a graph of the log function. This is the natural log function, and you can see how, although it grows very quickly near 0, it very quickly begins to level off, and its slope gets smaller and smaller as we continue. This behavior at the start is due to the fact that e to a very big negative power will give us a very small number close to 0. So near 0, the natural log takes on these big negative values, and then it shoots up and levels off. And this is convenient. Now that we can actually see the natural log function, we could hazard a guess at what its derivative looks like by just eyeballing some of the slopes. Near 0, what are the slopes of the natural log function? Well, they would be very large positive numbers. The function's very steep here. They would be numbers like this. They start to get a bit smaller as we go forward on the x-axis, and it starts to level out a little bit, so these slopes decrease. And then as we go further and further, the slopes get ever smaller, so they start to approach 0. So the derivative of the natural log function then might look something like this, and this is something you might recognize. Indeed, this is 1/2 of the function 1 over x. This is a graph of 1 over x. One big thing you know with 1 over x that makes it different from the natural log function is that for 1 over x, negative inputs are perfectly valid. Sure, for 1 over x, we definitely can't input 0, just like with the natural log, we can't input 0, but there's nothing wrong with plugging a negative in here, and you can see that part of the graph in the third quadrant. Setting that aside for a moment though, indeed it is the case that the derivative of the natural log function is 1 over x. And that then takes us to the thing that's being taught universally incorrectly, which is the antiderivative of 1 over x. What the heck should this be? If you've never learned this stuff before, then it's worth sitting a moment and pondering this question. What is the answer? What's the antiderivative of 1 over x? Probably the worst answer to this question would be to say we just figured out that the derivative of ln x is 1 over x. So if we go the other way, the antiderivative of 1 over x, well, certainly that would have to be the natural log of x, and then we want to make sure we throw in that arbitrary constant, because adding a constant, shifting the function up or down, doesn't change its slopes, and thus doesn't change its derivative. There's a big problem with this answer, though. Here, it is the case that the derivative of the natural log of x plus c, wherever it's defined, is 1 over x. But if we're specifically asking about the antiderivative of 1 over x, we would like an answer for the entire domain of 1 over x, which is all real numbers not equal to 0. And the natural log of x cannot take the negatives, so this doesn't answer the question for all valid x values with 1 over x. So we'll put a little strike through there and consider a better answer. The better answer, which is typically given and which the OP is taking an issue with, is the natural log of the absolute value of x plus c. This answer has the same strength that this answer does. If x is positive, the absolute value doesn't do anything, and so of course the derivative of this thing is going to be 1 over x. Just like with 1 over x, we still can't plug x equals 0 in here because the absolute value of 0 is 0, and ln 0 is not defined. But in the case of a negative, now we can plug negatives in because the absolute value will make it positive, and so then the natural log will be defined, plus c, it all works out. Here, in fact, is a graph of the natural log of the absolute value of x. This is with c being equal to 0. And you can see for yourself how the slopes of these two disconnected halves of ln absolute value of x match up with those two disconnected halves of 1 over x. Zooming out so you can see them both at once, indeed, the derivative of this function at all of its points is equal to this one. And keep in mind that when we talk about the derivative, we think about x increasing. That's why the derivative, 1 over x, over here is negative, because the slopes here are actually negative. X is going from left to right, so even though you might say, oh look, it's going up, well no, we don't want to think about it in that direction, we want to think about it in this direction. So over here, its slope is slightly negative, which we see in 1 over x. Now that we understand this good answer answer to the question of what's the antiderivative of 1 over x, we can see the OP's issue. The absolute value is a nice shorthand for a piecewise function, so this function is behaving differently depending on the value of x. If x is positive, it behaves one way. If x is negative, it behaves a different way because of that absolute value. And of course, you can see that behavior manifest visually in the graph. We could write this function out a bit more explicitly without the absolute value notation. It would look like this. The function is the natural log of x plus c in the case that x is positive, so nothing has to be done to x. But when x is negative, what does the absolute value do? The absolute value hits it with another negative to flip its sign back to positive. So this is the behavior of the function when x is less than 0. And now the trouble becomes apparent. Remember how we said this constant doesn't change the slopes. That's why we write it. Because unless we're solving a problem that has given us additional information to pin down the value of this constant, when we take an antiderivative, we don't know what the constant is, so we make it arbitrary to account for all possibilities. But because this function has two disconnected halves, there's actually room for two constants, this one where x is positive, and this one where x is negative, and there's no reason that these constants have to be the same. Of course, shifting a function up or down doesn't change its slopes, but since these functions are disconnected, we could shift this one up and this one down, and still the slopes would all be the same. Thanks to this, what we call discontinuity in the middle at x equals 0, we have more flexibility with these constants that aren't reflected in the traditional answer of ln absolute value x plus c, and that's the OP's problem. I said before that you don't actually need to know the natural log function to understand this, because there's nothing special about natural log. You can see how 1 over x has the same exact thing going on here. Indeed, we could consider this technical issue on any function and its antiderivative where there's a discontinuity. So is the OP right that this is an issue, that this is a technicality that is simply glossed over universally when teaching calculus? Or perhaps is there something more going on here? Well, one perspective you might take is that the way it's often taught is technically incorrect and the OP's explanation is superior, but it really doesn't make a big difference. We see Wada Snack here weigh in, justifying exactly this perspective. Considering that most people, even engineers and mathematicians, get on just fine without the distinction, I can see why one wouldn't confuse the subject by talking about a small technical distinction. There is, of course, when teaching mathematics, especially at the high school level, always a delicate balance between enough rigor to be accurately representing the mathematics, but not so much rigor to overburden the students with more information than they really need to learn the key details of the subject. Of course, some people will take a pretty big issue with glossing over technical details in mathematics. Someone replies here, to be fair though, if this is seen as confusing the subject, this means that we're content with math being just a collection of formulas to be memorized and nothing more. Bit of a leap. I have to agree. Whether or not this particular aspect of glossing over technicalities is justified, I wouldn't say that accepting it means that we're content with math being just a collection of formulas. It just means we walk a delicate line, and teachers have to make the choice of including and excluding material one year where they might have done something different the previous year based on the group of students they have, the pace of the class, many extraneous factors regarding the school year. Sometimes they'll make the right choice, sometimes the wrong choice, but there's certainly a discussion to be had. Thankfully, anyone among the group of those universally teaching this incorrectly, if you have the perspective of just, it's fine, the distinction really is not that important, in an actual use case, we would be dealing with one half of the interval or the other, so the potential for different constants across them is really not relevant. There is a more formal justification for this explanation. We only need one constant because that's just built in to the convention of this notation. Indeed, this is not taught universally incorrectly. The details aren't ignored across the board. Just look at the most famous and popular calculus textbook in the United States, James Stewart's Calculus. You know what? Just for kicks, let me roll a die to decide what edition of the book to use. Oh boy, the first edition, my favorite. So here in the first edition, we can flip to where they talk about antiderivatives, and we'll see that Stewart's Calculus, the book out of which many teachers teach calculus, does address this concern, and this is also included in newer editions I have checked. The most general antiderivative on a given interval is obtained by adding a constant to a particular antiderivative, that's the plus c. We adopt the convention that when a formula for a general indefinite integral is given, it is valid only on an interval. As an example, the antiderivative of 1 over x squared is negative 1 over x plus c. These functions are both defined on two separate intervals, the negative reals and the positive reals, so there's room for two distinct constants. However, the convention is to just write plus c with the understanding that we're talking about a single interval. We don't necessarily know which one, which is why in the natural log case we have the absolute value bars, so it could be the negative interval, it could be the positive interval, either way this works, but the constant just applies for that one interval. No doubt many teachers are giving this answer and are not aware of this technical distinction. One person replied, "Wow, even after teaching about a dozen calculus courses, I had never thought about this subtlety. Unlike the majority of commenters, I feel that this is a really interesting discussion to have." It's always fun to just see a nice positive comment like, "Oh, I learned something," instead of all the bickering. Teachers who are unaware of this distinction and have just been using this answer can rest easy knowing that all they need to do to correct for the details is explain the convention, just like Stewart's Calculus does, that when we write that plus c and give this antiderivative formula, we understand that it applies only on a particular interval. It may be the positives, it may be the negatives, other functions, we may have different intervals to consider, but it's only on a single one of them. If for some reason we needed to consider the antiderivative across separate disconnected intervals, then we might want to allow for separate constants. I'll take this precious first edition back into my vault and we can look at a couple more replies. From what I could tell, this first reply that said it's fine and not a big deal is definitely the one that triggered the most arguments. How else can people demonstrate their pedantic knowledge on Reddit unless we care about this technical distinction? I feel like on Reddit and just the internet as a whole, people will very often give you the worst faith interpretation of all of your words. The OP is saying, "Hey, I keep seeing this thing taught a certain way, and I realize that if you pay attention to the details, it doesn't seem quite right. What's the deal with that?" But of course, to some, it's going to come across like one big, actually. Of course, a lot of people care deeply about these details. It's the difference between correct and wrong. You know what? Let's just leave off the plus c part entirely. If it doesn't matter, that's a small technical distinction, right? While we're at it, let's just assume all functions are continuous. That'll make things simpler, and most students will never need to know the difference. We're certainly seeing the delicate line issue here. If we start to leave off technical details, I mean, how far do you go with that? What other things can you just ignore if you're content to ignore some things? Again, this particular issue can be resolved completely by notational convention. Understanding an antiderivative formula with the plus c just applies to a particular interval. But anytime teachers are content to ignore technicalities, understandably, mathematicians get worried. Someone else mentions a time where this issue was indeed relevant to their grade. They were asked to solve the differential equation dy dx equals 1 over x, and here the domain is explicitly specified. In this case, the answer, the antiderivative, needs to cover the entire domain, that's all the reals excluding 0, and so it would make sense that you would need to point out the potential for those two different constants. Just writing ln absolute value of x plus c implies that you're only considering this on a single interval, but of course this function is defined on two disconnected intervals, and so this wouldn't really be a sufficient answer to this question. I always find it amusing too to see people who just refuse to engage with the issue at all. It's the same, it's correct. ln absolute value x plus c. This is just simpler. There you go. It turns out that we never had to make such a fuss about it in the first place. Several people also mention an alternative way to make this issue go away, which is to think of c not as a particular number value, but as a function that's locally constant. So it could be one constant value on an interval, but then on a separate interval, it could take on some other constant, so it holds constant values, but only across particular intervals. If c is a locally constant function instead of just a constant value, then it has every right to be different across distinct intervals. That, of course, isn't how students are generally taught to think about the plus c, but it does settle the issue. But regardless, I thought this was an interesting discussion and a nice excuse to hopefully introduce some people to a little bit of calculus and the natural log function. I'll be curious to see in the comments how you were taught about the antiderivative of 1 over x, and if this issue with the different constants was addressed at all by your teacher. If you had never considered this technical distinction before, hopefully this helped fill a little gap in your knowledge. And if there's a gap in your wardrobe where some beautiful math shirts could go, check out my math fashion brand, mathshin.com. This is our most popular item, the Pigeonhole Principle t-shirt. It's a shirt demonstrating a classic principle from combinatorics called the pigeonhole principle, and the pigeons look like famous mathematicians. We've got Leonard Euler, Carl Gauss, Pierre de Fermat, Euclid, and the Bernoullis. There are 3 other awesome designs and a bunch of other cool products, hoodies, everything you want on mathshin.com. Check it out, link in the description and the pinned comment. Would really appreciate you picking up a product. Let me know in the comments if you had any questions, and be sure to subscribe for more of the swankiest math videos on the internet.
I'm unstable, revealing art to keep the cable cut and unsort the table. If Texas Instruments don't reply, I think this time it might be fatal. Wish to sell my own fake, cause I'm jaded.
Hate the odds that I calculated.
Press and pull and pray and push it all the way through the whole blue
Planet faded.
psychosomatic habits. Why you so